Hi guys, welcome to this vodcast on equilibrium, in particular three forces in equilibrium. It is the final chapter in the book that is mechanics. It should be a bit of a recap, and speaking of recap, let's start with a couple of refresher problems to get you going. So let me just get rid of my mug. You don't need to see it. Here's a question, have a go at it. A particle of mass m is projected along a horizontal line from the origin with a speed of v. It is acted upon by a resistance kV newtons when the speed is equal to v. So because it's moving in one direction, we can align velocity with speed. Find the velocity after the particle has traveled a distance x. So you need to find that connection between v and x given the initial information. I'll let you have a go. Please engage in the problem, and then when you're ready, come back and we can have a look at the solution. Okay, you're back. So you've had a go at the problem, and you can see, hopefully most of you would have seen, it's all about, okay, hang on a sec. Let's see if this is going to work for me. Yes, it will. Okay, so here's your object. It's been initially released with a speed of v in that particular direction, and there's no force enabling it to continue to move in that direction. So that's the direction of motion, but it's experiencing a resistive force proportional to its velocity or speed. That's what's going on, and of course it's mass. So you've got your weight force, and being connected to a plane will have the normal as well. So they're all the forces. It's only three forces in play. Now it's not constant acceleration, it's a variable acceleration, but of course it's modeled in terms of a variable force. So force equals ma will be equal to nothing, no force in the direction of motion, minus kv. And then, of course, what do? We divide through by m. So let's just separate those constant parameters. And what is the connection required? We need to find a relationship between v and x. So it's not a is dv dt. What's the next logical choice? That's right, a is equal to v dv dx. And of course that's minus k on m v. dv dx is therefore equal to simply that constant. All right, from there you should be right. Let me just get rid of all of that. I've got probably something much neater, I'd imagine. So let me erase, and let's see what the rest of the PowerPoint has entailed. Okay. All right, click. Oops, no, we don't want that. All right. Okay, there it is. Constant dv dx, we anti-derive. We're left with that particular expression. We know when x is equal to 0, v is equal to capital V, therefore c is equal to capital V. And we've got our relationship between velocity and distance. So hopefully you were good with that. All right, second of the two problem starters. This is a lovely problem. You can see there's a pattern to this problem that we've seen before on an inclined plane or a horizontal surface. This happens to be a pulley and a different kind of connected body system, but it's very, very similar to the sort of problems you've seen before. So hopefully you'll be fine with it. What are we talking about? We're talking about a pulley with three masses connected. Obviously, it's going to be moving down in this direction, y, because 5.2 kilos is greater than 2.8 kilos. So that's the direction in which the connected body system will be moving. And of course, part A is fairly standard. Find the acceleration of the masses. Part 2, find the tension between the 3 kilo and the 2 kilo mass. So of course we're labeling it in those particular directions. Okay, and part B is the interesting one. The string will break, so the tension must be so great that the string breaks between the 2.2 and the 3 kilo. and what we need to do is work out how much further will the 2.2 kilo object continue to fall in that direction, in the direction it was moving initially, before the deceleration causes it to slow and stop. So we'll talk about that later. I'd like everyone to have a go at this problem independently. So pause this vodcast and then return for a solution. Okay. All right, I take it everyone's returned. They've had a go at the problem. A is, of course, a bit of a standard problem. You could do it everything mass by mass, and I'm very happy for you to do it. But of course, you should also recognize there's 3 plus 2.2, 5.2 G is pulling the system as a whole. So we're analyzing it as a system as a whole. And it's being retarded by the weight force of the 2.8 kilo mass. And that's going to be equal to the total mass of the system. 2.2 plus 2.8 is 5. 5 plus 3 is 8. 8A. So what have we got? We've got 2.4 G equals 8A. Therefore, A, there's 3 lots of 0.8 and 2.4, so is equal to 3G over 10 meters per second squared. That's the system as a whole. Okay. Now, if you wanted to analyze it mass by mass, there's quite a lot going on there. There's, of course, 3G pulling it downwards. We've got 2.2G, the weight force, and we've got 2.8G. And then you'd actually come up with 3 separate equations and come up with the same end result. So, all right, the tension. All right, now the reason why I've gone, actually, let me just go and rub out what I've just added there to avoid confusion. All right, let's get rid of that and that and that. Okay, lovely. All right, so let's just have a look at the 3 kilo mass, because that's enough for us to work out the tension in the system. We now know its acceleration, and if we just look at the 3 kilogram mass, we've got 3G is the weight force being retarded by a tension force, and that's equal to mass times acceleration, 3A. So A part II, we're just focusing on the 3 kilo mass. In A part I, we're looking at the system as a whole. So, okay, tension is equal to 3G minus 3A. So that's going to be equal to 3G minus 9G on 10, or 21G over 10, or 2.1G, whatever you like. Okay, so that's A part done. Let me just erase all of this. Give me a moment. Okay, get rid of it. And I might just click through because I've probably got working out on all of this, I would say. All right, yes, let's, actually, no, oh well. All right, there we go. Just bear with me. Rubbing. Why aren't you rubbing out over there? Okay, rubbing, erasing. Okay, there we go. There's probably a more efficient way to do this. I don't know. Okay, let's just clean it up. Nice. Okay. All right, back to the pen. All right, so the string has broken. Okay, the system started at rest, and after 1.5 seconds, it was allowed to fall, and then a break occurred. Okay, so that's the situation. So it's continuing to move in this direction, in the original direction of motion, but then it's going to experience a deceleration. Why will it experience a deceleration? Because 2.8 kilos is greater than 2 kilos, and it will start to slow, stop, and then move in the opposite direction. But what we're after is how far it does fall before it does come to a rest. Okay, in fact, let me just click on the previous part. Okay, so that's the information we've already obtained. Have a think about what's happening in part 2. In order to work out how far it falls, we know its time. We know S is what we need to find, the distance it falls. So what do we need? What are the missing elements? We need the acceleration under this changed circumstance. So, and we've got that from our F equals ma. So we've got 2.2g in the direction of motion being retarded by 2.8 g, so a negative acceleration, is equal to the total mass of the system is 2.2 plus 2.8, which is 5 a. So what we've got is, of course, negative 0.6 g equals 5 a. So therefore a is equal to minus 0.12 g. Okay, good. All right, that's the deceleration under this changed circumstance. So we've got the time it's taken. The time relates to the first situation. So okay, situation 2. This is the deceleration. We need to work out the distance it falls under this situation. What do we need to borrow from situation 1? And that's right, we've seen this many, many times. It's velocity. So we need to go back and work out what speed it obtained after 1.5 seconds. So maybe I'll just click on it from here on in. So from situation 1, you can see we had our acceleration from equation 1. Let me just change the color. From equation 1, we had our acceleration of 0.3 of g. You can recall from our previous example, it starts at rest and it runs for 1.5 seconds. So we've worked out our speed that obtains. So I might just have to clear this in order to keep going with the PowerPoint. Okay, clear, clear, clear. Okay, and then if I keep clicking, keep clicking. Okay, so in situation 2, there it is, 0.12, negative 0.12 acceleration. So we now know its initial speed. So the final speed after situation 1 becomes the initial speed in situation 2. We know its deceleration is minus g on 6g on 50, or minus 1.2 g. And we also know the final velocity is equal to 0, and it's all about finding s from there. So you know which equation it is, of course, v squared equals u squared plus 2as, and you can work out the distance. Have I done it? Let's have a click. I haven't done it, but I've set it up for you to find. So it's obviously going to be equal to minus u squared divided by 2 times a, and that's how you find your distance. So I'll let you guys finish it off because I've run out of space to work on. So that's the second of our 2 problem starters. You can see the pattern in these problems. There was seen in various guises this transition from one situation to the other, and what we have to do is determine the speed that it obtained, the velocity it obtained at the end of one situation becomes filtered in as initial speed or initial velocity in situation 2. Okay, this leads us to the main thrust of this vodcast, equilibrium, in particular equilibrium with respect to 3 forces in a 2-dimensional plane. Okay, so just to remind ourselves, what is equilibrium? It's when the resultant force of all forces acting upon a particle is equal to 0. So you get a closed polygon of vectors. And of course, when there's three forces, you're getting a closed triangle of vectors. Okay, what does that mean? It means it's either one of 2 things. It's either static, it's at rest, such as a hanging mass, for instance, or it's moving with constant velocity. Don't forget that one, Newton's first law. Okay, now, of course, with three forces, you've got a triangle, and there's 3 particular techniques that we want to explore in this particular session, each with its own advantages and perhaps disadvantages. Okay, so here's the first technique, the triangle of forces. Of course, create that closed triangle with the understanding that if alpha is the angle between, say, force 1 and force 3, then in the closed triangle, what's the angle in the closed triangle? That's right, it's 180 minus alpha over there. Okay, and so on and so forth. So just remember how to transition between a force diagram on a particle and a closed triangle of forces. Okay, beta between F2 and F3, therefore 180 minus beta, and so on and so forth. Now, what's the advantage of this? With three forces, of course, it brings in all the mathematics that we know about a triangle, sine and cosine rule. There's a bit of a asterisk with the sine rule for finding an angle. Don't forget the ambiguity. We'll talk about that later. And of course, if it's a right angle triangle, beautiful, SOHCAHTOA, couldn't be easier. All right, hopefully this little table will help you identify when would it be appropriate to analyze the situation of equilibrium as a closed triangle of forces. Well, this is probably the main one. So suppose you've got three forces, the magnitude of three forces acting upon a particle. You're not given any information about the angle between them, and you're asked to find the angle between two of the three forces. So what approach would you use? You'd set up that closed triangle and then apply the cosine rule. And of course, using the cosine rule, what you're finding is not the angle between the two forces, but 180 minus that angle. So don't forget that. That's a little bit of a tricky part. Okay, now the other useful information, the other situation where you'd create a closed triangle of forces would be when the magnitude of two of the three forces is known, and so the magnitude of two of the three forces is known, and the angle between those two known forces is also given. What you need to do is find the magnitude of the third force. Again, it's very neatly set up for you to create a closed triangle of forces and then apply the cosine rule with respect to 100 minus alpha, the given angle between the two known forces. So certainly situation one is a bit of an imperative situation. There'd be no other way you could do it in the other alternative means we're going to discuss. But in situation two, you've actually got a choice. You could analyze it by other means, but this is probably the most efficient approach. So not entirely necessary like in the first situation, but would be the most efficient way to go. All right. Okay, so here's one such application that was suggested previously to creating a closed triangle of forces. We've got the magnitude of two forces given to us. What we need to do is find the magnitude of the third force, P newtons. Three forces acting on a body in equilibrium, perfectly set up for a triangle of forces. We're told that the angle between the two known forces is 50 degrees. What we need to do is find that P. All right, why don't you guys have a go? It shouldn't take you more than 30 or 40 seconds to get this done, maybe a minute, but it's fairly straightforward question. Have a crack, then come back to the vodcast when you're ready. Okay, I take it you're back and ready to look at the solution. First thing is set up a force diagram on the particle, and it should look something like that. Step two, obviously, if you create a closed triangle of forces, it should look like this, 180 minus 50, 130, and then straight up application of the cosine rule. So P squared is equal to 10 squared plus 10 squared minus 2 lots of 10 times 10, which we'll write as 10 squared, times cos of 130 degrees. Okay, let's just clean that up. And of course, don't forget, by the way, sometimes I even forget to take the square root, but then if I go back to the question, I might have an unusually large value. Presumably I have a value that would bring on a suspected derivation. So then I realize, oh, I forgot to take the square root, and off you go and take the square root. Okay, that should have been nice and straightforward. Okay, here's another example that relates to the previous discussion. We've got the magnitudes of three forces. We know that the resultant force is zero because the particle's in equilibrium. What we need to do is find the angle between two of those three forces. In fact, the angle between the 2 Newton and 4 Newton forces. Have a go, please. We've talked about this scenario before, but have a go, engage in the problem, and then pause the vodcast and then return to the vodcast when you are ready. Okay, you're back and you're ready to review the solution. First step is draw the diagram. In fact, that was part A. There it is. There's the force diagram. And what what we're doing is labeling theta as the angle that we need to determine. Okay, we convert it from a force diagram to a closed triangle of forces, and of course it's always going to be 180 minus that angle. All right, the only way to really find what that angle size will be is to apply the cosine rule, and of course cosine rule involves lengths A, B and C, where A lies directly opposite the angle of interest, and B and C are the other two side lengths. So what we're doing is unpacking the cosine rule to make cos of the angle the subject, and then finally the last step is to work out the actual angle by taking the supplement of what the cosine rule determines it to be. So there it is. So cos of 180 minus theta is 25 minus 4 16 plus 4 minus 25 divided by 2 times 2 times 4, and it leads us to that answer. Negative, clearly an obtuse angle. That obtuse angle turns out to be 108 degrees, but then the actual angle between the two forces as related to the original force diagram will be the supplement of that, pretty close to 72 degrees. Okay, creating that closed polygon or triangle of vectors is effective, but sometimes there's quicker and easier ways to go about it. And if you can recall from last year, not everyone learned about Lami's theorem, but there's Lami's theorem, and there's a bit of a cautionary tale about Lami's theorem, but it's certainly very easy to apply. And of course, our old friend resolving forces into an IJ convention based on an appropriate imposition of an XY plane upon the situation. Okay, if you've forgotten Lami's theorem, here it is. So here's the generalized situation. A force of magnitude R directly opposite an angle between P and Q of magnitude R, angle P directly opposite force of magnitude P, angle Q directly opposite a force of magnitude Q. When we create our resolved triangle of forces, closed triangle of forces, the sine rule suggests the following relationship is in play, but of course sine of 180 minus theta is equal to sine of theta. Therefore, it reduces to this simplified scenario, which means in a force diagram, the ratio of the magnitude of a force to sine of the angle opposite is equal throughout the system, and we can use that to find unknown lengths and angles, but of course there's a bit of an asterisk with finding angles that we'll discuss shortly. Okay, so here's one nice, beautifully set up for a very quick and easy application of Lami's theorem. Have a go. It shouldn't take you very long to work out the magnitude of P and Q based on a quick application of Lami. So have a quick go at it and then return to the vodcast. Okay, you've returned to the vodcast. That's 220, so obviously 140 degrees is the angle between Q and 10. Of course, what we're going to do first, we've got our base point, we've got a force of magnitude 10. We know the angle directly opposite it in the force diagram. From that one ratio, we can find out any of the unknowns that we need to, and that's really the basis for applying Lami's theorem. So from there, from the ratio of 10 to sine of 100, we know that the ratio of P to sine 140 will be the same as is the ratio of Q to sine 120, and we can find P and Q from there. So in order to apply Lami's theorem, you need a given angle between any two forces and the magnitude of the third force that's directly opposite that given angle. Okay, if that's in play, Lami's theorem is all good to go. Okay, all right, let's keep going. Caution, hello, let's remind ourselves about the sine rule. The sine rule is ambiguous, naturally ambiguous. So when you've applying Lami's theorem to find an unknown angle, and recall this is only for finding an unknown angle, unknown magnitudes of forces has no issues, so unproblematic, we need to caution our answer. Now, our CAS will always give us the acute angle. However, it may be that the actual angle between the forces is the supplement of that acute angle. So how do you make that determination? Well, generally, it's all about thinking about the physical situation and thinking about which is the more likely of the two. Now, if the acute angle that your calculator reads out is very close to 90 degrees, then say 87 degrees, so you've got choices of 87 or 93 degrees, this particular approach is really not going to work for you, and you should be thinking about an alternative way to analyze the problem. Okay, but when it's 30 degrees, 40 degrees, 30 degrees and 150, 40 and 140, there should be an obvious choice in the matter for determining the required angle. So let's have a look at that situation now. Okay, if the force diagram below captures a particle in equilibrium, find the angle between the 12 Newton and the 8 Newton forces. So find this unknown angle. All right, so is it meeting the brief for Lami's theorem? Okay, so we've got an angle and we've got the magnitude directly opposite. So we know that straight away, we know that ratio, the ratio of sine of 70 is to 12. In the same way, sine of theta is to 6. Yep. All right. So from there, we can obviously find what theta is. Theta will be the inverse sine of 6 times sine 70 over 12, so half of sine 70. Okay, and we get a particular answer. So let me just erase that, and then we can discuss the issues. So, okay, so there it is. Now, what the calculator will tell us is that the answer of theta is in fact 28 degrees. But then we need to just think, what makes more sense in this scenario? Is it 28 degrees, or is it the supplement of 28 degrees, 152? So this is how you think about it. If it was 28 degrees, then of course that 12 Newton would be pulling it in a direction somewhat like that. So if that was 28 degrees, 70 plus 28, an angle slightly bigger than 90. Now you can see if that was the case, it's impossible for this particle to be in equilibrium, because in fact it would be moving off somewhere in that kind of a direction. It couldn't possibly be in equilibrium. Okay, so what we need to do is realize, hang on, it's not in fact 28 degrees, the angle between the 8 Newton force, but it is in fact 152 degrees. So 152 degrees. Okay, so that's how you need to think about it. And as I said, if it was an angle very close to 90 degrees, then you've got to reanalyze the situation using alternative means. Okay, the third and final technique we've already discussed, and that's imposing an XY plane on the situation. Positive XI, positive YJ, and appreciating in a situation of equilibrium, our I components will cancel themselves out and result in 0, and our J components will cancel themselves out and result in 0. Okay, and this was really that process of imposing an XY plane and talking about resultant vectors was really the focus of 13A. So just to refresh your memories, this was an example that we had right at the start of this unit. So those three forces clearly do not result in a particle being in equilibrium, but we could actually use that technique to work out the magnitude of the resultant force. How can we do that? Well, we can just say, oh, that's not very straight, that's okay. There's our y-axis. There's our x-axis that will align with the 5 Newton force. And as we know, positive I, positive J, and we can just describe the sum of all those vectors in terms of i's and j's. And to take the magnitude, it's just simply square of the two components summed and square rooted, and the direction of the resultant force with respect to the square. We can talk about our inverse tan j over y over y. That's what we're doing back in 13a. When we apply it to situations of equilibrium, far easier. The i's cancel, the j's cancel. That's what it's all about. So let's just recall what that was about. So there's the components in the I direction once we've got positive x aligned with the 5 Newton force, and there's the components of the j force, the sum of the resolved parts running perpendicular to the 5 Newton force. So as I said, this is a repeat of what I've just referred to. So in that exercise, then we talked about a non-zero resultant force. We squared our I components, we squared our J components, sum them, take the square root to work out the magnitude of the resultant force. But in this situation, our resultant force has 0 magnitude. So we're expecting our I and J's to cancel themselves out. Okay, what does it mean to analyze a situation of 3 forces acting upon a particle in equilibrium? This notation captures it beautifully. So we've got 3 forces, F1, F2, and F3, because they're in a plane. We can analyze them in terms of I and J components with respect to our imposition of an XY plane upon the situation. And of course, if they are in equilibrium, it means the 3 forces sum to 0, to the 0 vector. And what does that mean? It means each of their I components, when summed together, equals to 0, and each of their J components, when summed together, is equal to 0. Okay, so that's effectively what we're doing in these particular problems. Let's apply that to this situation. What we have is 3 forces identical in magnitude and equally spread apart upon a particle. Clearly, it's going to you're going to create an equilateral triangle when you sum all of those 3 together. But a really neat way to show that the particle is in equilibrium is to just impose an XY plane in a manner convenient to us and show that the sum of the i's disappear and the sum of the j's disappear. So this is how you might go about it. So let's just suppose that that's our x-axis. This is going to be our y-axis, positive direction, and then when we start to talk about the resultant vector with respect to that imposition of x and y, we've got, of course, 10 in the positive y direction, so it's 10j. So we're going to take this vector here as a sum of its 2 components, one in the x direction, one in the y. So that's obviously 30 degrees in here, 30 degrees over there. So that's going to be plus 10 cos 30, cos 30 in the I direction, and the component of that force resolved in the y direction will be minus 10 sine 30 j, and then we go to the other side, resolved in the x, resolved in the y, so then it'll be minus 10 cos 30 I minus 10 sine 30 j. So there's our resultant vector. Clearly these I components are killing each other off, and the j components will do so as well. So because of sine 30 being 1/2 equals 0 vector sum. Now that's just a neat way to show that the sum of 3 forces is in fact in equilibrium. Okay, here's another problem similar to the last. So you've got 3 forces, the magnitudes of which are each given. You're told that the angle between those respectively, so obviously that respectively means 120 refers to the angle between the 10 Newton and the 5 Newton. 90 degrees refers to the angle between the 5 Newton and the 5√3 Newton. So draw a force diagram and then impose an XY plane as convenient. Now, of course, This is nice. We like to see 90 degrees. It makes our XY plane a bit of it guides our hand in how to set up the XY plane. I want you to have a go at this. See if you can show that the particle is in equilibrium via resolution of forces. Okay, you're back. So I assume you've already had a crack at it and you're looking for the solution. So first things first is to set up a force diagram. Obviously, the fact that two forces are running perpendicular to one another makes it very, very convenient to set up our XY plane. So why not, let's do it in this particular manner. 30 degrees over here. So of course, when I resolve each force with respect to the X and Y plane, we're looking at that kind of scenario. Okay, so clearly this is very similar indeed to the last one. All three forces would be 5J plus 5 root 3I, and then the 10 Newton force would be minus 10 cos 30 in the I, minus 10 sine 30 in the J, and you can see you'll get a nice cancelling of your I's and a nice cancelling of your J's, leading to a zero vector sum. Don't forget the tilde in that expression. It's just a neat way to show that the particle is indeed in equilibrium. Okay, so some final tips. We're going to look at just two more problems to close out the session. Lami's theorem, neat, easy, particularly when you have to find magnitudes of angles. You are restricted to a known magnitude of one of the three forces in equilibrium. Remember, Lami's theorem only applies to three forces in equilibrium. So when you know the magnitude of one of the forces and the angle directly opposite that force, Lami's theorem's good to go. Asterisk over finding an angle, but that's fine. You can still work through it if you can. Tip 2, resolving forces is easily the way to go when two of the given forces are running perpendicular. Setting up at the XY plane just becomes neat and easy. And the third thing is creating a closed triangle of forces. Easily, well, it's the only way to go when you're given the magnitude of three forces. You have to find a particular angle between two via the cosine rule, and it's also quite convenient when you've given two of the forces, two of the three, the magnitudes of two of the three, and the angle between those two forces, and you need to find the magnitude of the third force. Also, setting it up via the cosine rule, nice, neat, and clean. So, but three different techniques. Enjoy, use them wisely. Okay, so we're going to start to look at our two final problems. Okay, have a go at this problem. It usually causes a bit of grief, but see how you go with it. So the hardest thing is setting up the diagram. A particle of mass 2 kilos hangs from a fixed point, we'll call it O, by a light inextensible string of length 2.5 meters. Okay, it is pulled aside by a horizontal distance of 2 meters by a force P newtons inclined at an angle of 75 degrees with the downward vertical. Let me just highlight that. All right. Focus on that when you're coming up with your diagram, and it rests in equilibrium, so it's a static situation. Find P and the tension of the string. So guys, go and do your best to set up a force diagram of all the three forces involved in this scenario: the weight force, the tension force, the pulling force, and then see if you can go and find P and the tension force. Okay, so you're back, so I assume you're ready to explore this problem. Okay, so let's begin. So that's the diagram as I see it. So here's the point O. So there's the fixed point that it's attached to. Here's our string of tension force T. Now, the only time you're ever given length in a problem like this is when you is just a means to working out the angle. Okay, so we need the angle between all three forces. So just highlighting all three forces. Here's our weight force, 2G. Here's our pulling force, P. Now, of course, you can see it's being pulled in this direction away from the natural hanging position, which would be directly below the fixed point O, and it's been pulled to the side. So that's why P, with respect to the downwards vertical, runs off in that direction and not to the left. It must be to the right in the direction which it's been moved away from the being directly below O. Okay, so here's our third force, and that's a force, that's the string, and of course it's delivering a force on the particle via tension. Okay, and there's our theta. So theta is easily determined as via cos in our SOHCAHTOA. So it's the inverse cos of 2 over 2.5 adjacent over hypotenuse, which I ran through the calculator just a few moments ago, and it's roughly 37 degrees. Okay, now let's just leave it like that for explanatory purposes. So I should be actually using a more precise value, but let's leave it at that. Okay, so if that's the angle between them, I can actually work out P. Well, in fact, I know 2G, so I know 2G, the weight force, and I now know the angle directly opposite. So what would angle alpha be? So angle alpha, let's just think of it as 360 minus those angles, 360 minus 90 minus 75 minus 37, rounded up, and that turns out to be 155 and 37, 165 and 37 rather. So that's 202. So 202 minus 360 is 158 degrees. Okay, so what we've got is I can just set it up via Lami's theorem. Why not? Because I've got to work out the magnitude of a force, so unproblematic. So 2G is to sine of 158, as P would be equal to, as the ratio of P is to 90 plus 37, sine of 127. I can solve that ratio equation for P, and of course that's going to be the same thing as the tension force divided by sine of 75. All right, so I can, from this one ratio here, 2G is to sine of 158, I can work out P and T fairly quickly via Lami's theorem. Okay, welcome to the final problem of the session. So the angle between two forces, 10 newtons and P newtons, is 50 degrees. A third force of 12 newtons keeps this particle in equilibrium, so they all balance out. What we need to do is find the angle between the third force, the 12 newton force, and the 10 newton force, and then hence find P. Now the hint is as follows: find the resolution of the forces in a direction perpendicular to the P newton force. So guys, do your best with this. Pause it, have a crack on your own. Create that force diagram with the given information, but align your X and Y axis in line with the hint. So you need to find the resolution of forces in a direction perpendicular to the P newton force. So make your P newton force either your positive X or positive Y direction and take it from there. Okay, I'll be back with you in a sec. Okay, you're back. So hopefully you drew a diagram somewhat similar to that. Okay, so I'm just clearly imposing an XY axis on the situation. I've got my positive X, my positive Y, and I should be able to find out the angle between the 10 Newton and the 12 Newton force. Okay, how can I do that? Obviously that's 40 degrees, that's 50 degrees, and it just comes down to working out what this angle would be over here. Now, as suggested, it's in equilibrium, so the resultant force has 0I and 0J components. So the resultant force will be equal to Pi plus 10 cos 50I plus 10 sine 50J plus, so I'm calling that alpha, plus minus rather, let's just change that to a minus 12 cos alpha I minus 12 sine alpha j. But as said, all we're interested is resolving forces in a direction perpendicular to the p forces. So our j component really has the following elements to it. It has 10 sine 50, so I minus 12 sine alpha equals to 0, and from there we can work out what alpha is. So alpha will be the inverse sine of 10 sine 50 divided by 12, and we come up with our answer from that. So the angle will be 90. Sorry, why did I write 50 there? Sorry, it was 90. So the actual angle, required angle, will be alpha, whatever that turns out to be, plus 90 plus 50 degrees. Okay, now what will be the magnitude? Now that we know alpha, we can resolve things in the I direction. So let me just get a different color for our I direction. So P plus 10 cos 50 minus 12 cos alpha will be also equal to 0. And from there, we're able to work out what P is. So P plus 10 cos 50 minus 12 cos alpha. So will give us, setting that to 0. So let me just write that out for you in case you didn't follow. So P plus 10 cos 50 minus 12 cos alpha is equal to 0. And we know what alpha is by resolving forces in the j direction. That's it. It's a nice problem to finish with. Hopefully you got something out of that, and it's really pretty much a revision of skills and processes we learned last year. That's it for now. Enjoy dynamics. It's an awesome unit.